So today we're going to start a new chapter, which is the chapter of power series, chapter 6. So in section 6.1, we're going to start identifying what a power series is, and then we're going to talk about the radius of convergence and the interval of convergence for that power series, and then we're going to learn how to represent a function in terms of a power series. Okay, so let's start by defining what a power series is. So a power series is a normal series that looks like this. So it has a coefficient c of n, and it's multiplied by x to the n. So now if you plugged in the values of n, you're going to get c of 0, c1 x to the 1, c2 x to the 2, up to infinity. Now we call this a power series centered at x equals 0. Because here, x does not have any numbers subtracted from it. If we have a power series of this form, this is a power series, but it's centered at x equals a. So this is the main definition of a power series. It's just coefficients and then x to a certain power n. It's either centered at x equals 0 when you have x by itself, or centered at a certain number a if you have x minus a raised to the n. So let's look at these examples. If I have the summation of x to the n over n factorial, so this is obviously a power series since I have x to the n and something multiplied by it in terms of n. So here, this is a power series centered at x equals 0, and my c of n is just 1 over n factorial. Similarly here, a power series centered at 0, but my c of n is just n factorial. Now let's look at the third example here. I have x minus 3 to the n, so that's a power series, and it's centered at 3. So here it's always minus. If it was plus 3, for example, it would be centered at negative 3. And my c of n is everything that's multiplied by x to the n, or x minus a to the n. So I have 1 over 3 to the n over multiplied by n factorial. So that would be my c of n. Now what if we have the summation of x to the n by itself? This is obviously a power series with c of n is just 1. But if you remember, this is also a geometric series if we're taking the ratio r to be x. And if you remember from the properties of geometric series, if the ratio was less than 1, then my series converges. And if the ratio r, which is x here, bigger than 1, then it diverges. So let's keep that in mind and see how that connects to the convergence of a power series. So we say to test whether a power series is convergent or divergent, we have 3 cases. We can either have our power series be convergent at x equals a, divergent everywhere else. So converge at x equals a, diverge at anything that's not equal to a. Now here, this r is called the radius of convergence. So when the case, when we have the case where the series only converges at one point a, the radius of convergence is just 0. Now, what if the power series converges everywhere? So it converges for all real numbers. So it converges everywhere, and the radius of convergence here is infinity because it covers all real numbers. Now, the third case that could be possible is if we have a real number r, which is the radius of convergence, we can either have the series convergent at anything that's less than my radius of convergence, so my x minus a is less than r, or it diverges, so it converges for anything that's less than r, it diverges for anything that's bigger than r, and at x equals r specifically, I don't know if it diverges or converges. I need to test that value specifically and determine whether my series converges at that point or no. Okay, so any power series can only be one of these three cases. It could either converge at one point, or it could converge everywhere, or it could converge at a certain interval that we have. So I know it's a bit overwhelming. So let's try examples and see how that works. So let's start with a very simple example where I have x to the n over n factorial. Now, since we have n factorial here and we have exponents, I know to test the convergence, I need to use the ratio test. So testing the ratio test, I need to take the limit of a to the n plus 1 over a to the n. So this is my an plus 1, and this is my an. And if you do the keep change flip rule, you're going to get this. Now let's simplify. If we divide by x to the n, that's 1. If we divide by x to the n, I get x. And now since this limit does not have, it does not depend on x, I can take x with the absolute value outside of my limit. And then the n factorial obviously cancels out, and I get 1 over n plus 1 as n goes to infinity. Okay, now if we solve the limit, this is just going to be 0. And remember, from the ratio test, if the limit is less than 1, this means it converges. But here, it converges for any value x. So no matter what the value of x here, I'm still going to get a 0, which means my series converges for all values of x. So here, no matter what value of x I put here, I'm still going to get a 0, which is less than 1, so my series converges. So here, this series converges for all x. Then the interval of convergence, it's going to be all of that values of x, which is from negative infinity to infinity. And when we, and like in case 3, when it converges for all real numbers, then the radius of convergence is infinity. Okay, now the second example, I have n factorial multiplied by x minus 2 to the n. Obviously, this is a power series. I have factorial and exponents, so I'm going to use the ratio test. Again, a n plus 1 divided by a to the n. When we simplify, we're going to get n plus 1 and x minus 2 to the n as, without the n, as n goes to infinity. Again, since it does not depend on my x, I can take it out. And now once you evaluate the limit, you're going to get infinity. So here, since I got infinity, which is bigger than 1, the ratio test tells me that this series diverges. So this series diverges for all x not equal to 2. Because if x is equal to 2, I'm going to get a 0, which converges. So here, diverges for all x other than 2, and it converges for x equals 2. Now this is the first case. When we have convergence at only one point, then the interval is just a single point at x equals 2, and my r is just 0. And for the last example, I'm still going to use the ratio test and doing keep change flip rule. I'm going to get these two fractions. If we simplify, I'm going to get absolute value of x, the limit of n plus 1 over 2 n plus 2 as n goes to infinity. And now if you solve it by any method of limits, here L'Hopital's, for example, works, I'm going to get the absolute value of x multiplied by 1/2, so it's over 2. Okay, so here I'm going to have different cases. because this is number 3 here. I'm either going to have it less than my radius of convergence, bigger than, and then I'm going to test it when it's exactly equal to my radius of convergence. So here, since this is a ratio test, this always has to be less than 1 or bigger than 1 or equal to 1. So let's review. When we did the ratio test, the value of the limit, if it was less than 1, then by the ratio test, it converges. Okay, so let's just simplify this. So this is the absolute value of x is less than 2 if you cross multiply. So we know when this is true, by the ratio test, the series converges. So here, converges, the power series converges. And if you remember the properties of absolute value, it's going to be between -2 and 2. So here the radius of convergence is 2. Okay, now let's see what happens if the value of the limit is bigger than 1. So if it's bigger than 1, by the ratio test, it diverges. So again, if we rewrite it, and now if you use the properties of an absolute value, this is x less than -2 or x bigger than 2, and the series diverges there. And lastly, we need to check what if it was equal to 1 exactly. From the ratio test, we know that the test is inconclusive when the limit is equal to 1. So here, we need to test each point separately. So the values that satisfy this equality are x equals 2 and x equals -2. Since if you plug in 2 here, you're going to get 2 over 2, which is 1. And if you plug in -2, it's also going to be 2 over 2, which is 1. So let's test each point separately. So if x equals 2, if I replug it into my series, so let's remember our series is x to the n over n plus 1, 2 to the n. If we plug in 2 instead of x, we're going to have the summation of 2 to the n plus 1, 2 to the n. If we simplify, we're going to get the summation of n plus 1 in the denominator. Now, if you look at it, this is a harmonic series, and remembering the properties of harmonic series, it diverges. So when x equals 2, my series diverges. How about x equals -2? Doing the same exact thing, I'm going to get -2 to the n over n plus 1, 2 to the n. If you simplify, this is -1 to the n over n plus 1. Now, if you look at it, this is an alternating series with b of n 1 over n plus 1. Try and apply the alternating series test. You're going to see that this converges. So at x equals -2, my series converges. Okay, so let's review. When the absolute value of x was less than 2, which means x is between -2 and 2, the series converged. When it was bigger than 2, less than -2, my series diverged. And when x was 2, the series is divergent. When x is -2, the series is convergent. So the interval of convergence would be from -2 closed up to 2 open. My series is convergent, and my radius of convergent is 2. So these are the 3 cases for the convergence of a power series. You can either have it convergent at exactly 1 point, convergent at all of the points, or convergent for a certain interval, and you need to test the endpoints. So the last thing that we're going to talk about today is representing a function as a power series. So if I have a function, I want to represent it as a power series. So let's recall the geometric series first. If I have the summation of a to the r of n, we know that this is convergent if the ratio is less than 1. And if you remember, it converged to a over 1 minus r, which means that my series, which is all like a geometric series, but it's also a power series, is going to be equal to that. So here, the goal is I want to represent my function as this form of a geometric series, like the value of the geometric series here. I want to represent it this way, and once you represent it that way, you can easily get it into a power series. So for example, if I have a very simple function, 1 over 1 minus x, this is already of the form a over 1 minus r. So here, a is 1, r is x, so I can easily write it as a summation, right? So here, a is 1, so that's 1, multiplied by r, which is x, to the n. So this means that my function, which is 1 over 1 minus x, is just the summation of x to the n. Now this is pretty simple. My function was already in the form of a over 1 minus r. What happens if my function was not exactly in that form? Let's look at these examples. So now we want to represent the function in terms of a power series, and we want to find the interval of convergence. So here I have 1 over 1 plus x to the 4th. It does not look quite like the form that we have because I have a plus here. So the main goal when you have like a function, the two main things that you need to look for is I need to have a negative before my ratio, and this always has to be 1. So these are my two main problems. If I'm able to get a 1 and a negative, I should be able to transfer my function into a power series directly using the geometric series. So here, let's remember, negative times a negative, that's a positive. So here, if I do 1 minus x to the 4, we're still getting the same value, but I was able to get a 1 minus a certain ratio. So now I got it in the form of the value of a geometric series. So this is just the summation, and here a is just 1, so that's perfect. You take the ratio, which is negative x to the 4, raise it to the n, and n is equal from 0 to infinity. I'm just applying this rule here. Oops. I'm applying this formula that we got from the convergence of a geometric series. So that's why I was able to go from this into this. So now this is convergent whenever negative x to the 4th, which is my ratio r, is less than 1. If you simplify, the negative goes away from the absolute value. If you take the 4th root, then the absolute value of x is less than 1. Properties of absolute value, this is between negative 1 and 1, which means that the interval of convergence is just between negative 1 and 1. So now if you want to actually write your function as a power series, this is the summation, and now we can distribute the n, negative 1 to the n, x to the 4n, n equals 0 to infinity for x less than 1. So it's all about getting your function into the form of a geometric series. Okay, how about this function here? Now here, we have a different problem. I already have the negative, which is perfect, but I don't have a 1. I have a 2 here. So I need to get it into a 1 to be able to apply the geometric series. So I don't mind the x cubed here. This is just my a, or if you want, we can take it on this side. And then I want to take 2 as a common factor, because when you take 2 as a common factor here, you're going to get a 1. So if I take 2, now if you take 2 from the first term, you're just getting a 1 minus. Now I don't have a 2 in this term. So when you don't have something, you need to divide by it. So that's x cubed over 2. So now this here is in terms of a geometric series. I can easily take it, like represent it as a geometric series, because r is x cubed over 2. So keep this on the side. This part here, it does not affect me. Then this thing here is r to the n, as n goes from infinity to 0 to infinity. Now let's see. If we distribute, this is x 3 to the n over 2 to the n. Now since your summation does not depend on x or 2, you can take this and put it inside and multiply. So when you multiply, you have the same base, you add the exponents. Same base, you add the exponents. So that would be your geometric series, or like a power series. Now this converges f and only f, your r, which is x cubed over 2, is less than 1. If you cross multiply, then the x cubed is less than 2. If you take the cubic root, then it converges when x is between negative cube root of 2 and then the cube root of 2. So that would be your radius of convergence. So your function can be represented as this power series, for x less than the cubic root of 2. So it's all a matter of manipulation of, oh, I have a certain function, how do I get it to the form of a over 1 minus r? So main 2 goals, I need to have a 1 here, I need to have a negative here. So yeah, that would be it for section 1. These are some suggested problems, and you can do some of the Lumen Homework 5 too. If you have any questions, please email me and let me know if I can help you with anything. Best of luck.